back to my class in statistics. For today, we will discuss how to find the deciles and percentiles of ungrouped data. And as we have learned from the past lessons, deciles are numerical values that divide a distribution of data or a set of data into 10 equal parts. That means we need 9 points in order to divide a set of data into 10 equal parts. And each of the 10 equal parts represents 1/10 or 1/10 of the set of data, or that's equivalent to 10%. Now the percentiles, as we have also learned from the previous lesson, divides a set of data into 100 equal parts. And we need 99 points or values to divide a set of data into 100 equal parts. And each of the 100 equal parts represents 1% of the set of data, or 1/100 of the set of data. For the ungrouped data, we calculate the deciles, the percentiles, and the quartiles using the following formula. To find the deciles of ungrouped data, we use the formula k/10 multiplied by n plus 1, where k here is a numerical value between 1 and 9. And the denominator is 10 because the deciles divide the set of data into 10 equal parts. And n here is the number of values in the given set of data. If we want to find the percentiles, the denominator will change from 10 to 100. And as we have learned from the previous lesson, to find the quartiles of an ungrouped data, the denominator will be 4 instead of 10, because the quartiles divide a set of data into 4 equal parts. For our example on finding the quartiles of ungrouped data, consider the following values. We have 57, 68, 71, 74, 79, 81, 83, 86, 89, 90, 93, 95, 97, 98, and 100. In this example, the given values are already arranged in ascending order. That is, from the lowest value, from the smallest value to the highest value. If your set of data is not arranged in ascending or descending order, the first step before you proceed to find the deciles or percentiles or quartiles of the given set of data, you have to arrange first the given set of values in ascending or descending order. For the set of numerical values, we find the third decile. The third decile is denoted by d sub 3. And for the third decile, we take k is equal to 3. And n is the number of values in this set of data. The number of values is 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now we compute k/10 multiplied by quantity n plus 1, where k is 3 and n is 15. If k is 3 and n is 15, we have 3 over 10 multiplied by quantity 15 plus 1. And 15 plus 1 is 16. Multiplied by 3 is 48. Divided by 10 is 4.8. So this should be 4.8. Or 16 divided by 10 is 1.6, multiplied by 3 is 4.8. 4.8 means that the third decile is between the fourth and the fifth value. The largest integer that is less than 4.8 is 4. And the smallest integer that is greater than 4.8 is 5. Thus, we say that the value of the third decile is between the fourth and the fifth values in the arranged set of values, arranged in ascending order from the lowest to the highest. And from the lowest value, we find the fourth value, 1, 2, 3, 4, 74. And we also find the fifth value. From the lowest, we count 5, 1, 2, 3, 4, 5, 79. Hence, we say that the value of the third decile is between 74 and 79. Now, we actually find the value of the third decile. Because the third decile is between 74 and 79, we are sure that the third decile is greater than 74. So to 74, we will simply add some numerical value. And this computation shows us that the third decile is 3/10 of the distance between 79 and 74. The third decile is greater than 74 and is 3/10 of the distance between 79 and 74. So we get the distance between 79 and 74, and that is given by 79 minus 74. And we multiply this distance by 3 over 10. For this calculation, you can simplify this mentally. 79 minus 74 is 5. Multiplied by 3 is 15. Divide by 10 is 1.5. So to 74, we add 1.5 and we get 75.5. The value of the third decile is 75.5, and it is between 74 and 79. Now we check. The third decile means that 30% of the sample, or the number of values, which is 15, is at most less than 75.5. So we compute 30% of 15. The interpretation of the third decile says that at most 30%, 30% is 3/10 or 3 over 10 converted to percentage by multiplying 3 over 10 by 100% and you get 30%. And at most 30% of the sample size or number of values, which is 15, is less than the third decile of 75.5. And we compute 30% of 15 30% is 3 over 10. Again, we can find this mentally. 15 divided by 10 is 1.5. And multiply by 3 is 4.5. 30% or 3 over 10 of the number of values 15 is 4.5. Rounded up to the nearest whole number is 5. This means that 5 values maximum, the greatest number of values or the largest number of values that should be less than the third decile 75.5 is 5. That is what is meant by at most 30% of the sample size or the number of values 15 is less than 75.5. Or 30% of 15 is 4.5, rounded up to whole number is 5. A maximum number of 5 values is less than 75.5, the third decile. This means that you can have 5 or 4 or 3. That is what is meant by at most 5. Now we actually count how many values are less than the third decile 75.5. And it should be 5 or less. 75.5 is between the fourth value 74 and the fifth value 79. And the values less than 75.5 are 74, 71, 68, and 57. And we have 4 values. And this is satisfied. 5 values maximum are less than 75.5 or the third decile. And we actually have 4 values that are less than the third decile of 75.5. If 30% of the values maximum are less than the third decile 75.5, it also means that 70% of the values or the sample size are greater than 75.5. We take another example. We now find the 7th decile for the same set of data or values. The 7th decile is denoted by d sub 7. And for the 7th decile, we take the value of k as 7. And we compute k over 10 multiplied by quantity and plus 1, where k now is 7 for the 7th decile, and n is the same, which is equal to 15. We have 7 over 10 multiplied by 15 plus 1. 15 plus 1 is 16. We multiply 7 by 16 and then divide the product by 10. Or divide 16 by 10, that's 1.6 multiplied by 7. Sixteen divided by 10 is 1.6 multiplied by 7 is 11.2. 11.2 means that the value of the 7th decile is between the 11th value and the 12th value. The greatest or the highest integer that is less than 11.2 is 11. And the smallest integer that is, or the smallest whole number that is greater than 11.2 is 12. And we say that the value of the 7th decile, d sub 7, is between the 11th value and the 12th value in this ascending order of values. Now we find the 11th and the 12th values. And from the lowest value in this ascending order of values, we count 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 93. And we also find the 12th value. We count 12 from the smallest value, 57. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 95. Thus, the 7th decile that we are looking for is a numerical value between 93 and 95. The 7th decile is greater than 93 and is between 93 and 95. So to 93, we add some numerical value which is equal to 7/10 of the distance between 93 and 95. The value of the 7th decile is greater than 93 because it is between 93 and 95, so we are sure the 7th decile is greater than 93 but less than 95. So if the 7th decile is greater than 93, we should add some numerical value to 93, and that numerical value is 7/10 of the distance between 93 and 95. The 7th decile means that value, d sub 7, is 7/10 of the distance between 93 and 95. Between 93 and 95. So to 93, we add 7/10 of the distance between 93 and 95. And the distance between 93 and 95 is given by the difference between 95 and 93. And we find this value mentally. 95 minus 93 is 2. Multiplied by 7 is 14. Divided by 10 is 1.4. And plus 93, we get 94.4. Again, 95 minus 93 is 2. Multiplied by 7 is 14. 14 divided by 10 is 1.4. And 93 plus 1.4 is 94.4. Hence, the value of the 7th decile is 94.4. And it is between 93 and 95. Now, we check. We say that 70%, the interpretation of the 7th decile is that the 70% of the values in this ascending order of values, at most 70% of the values in the given set of numerical values are less than 94.4. Hence, we compute 70% or 7 over 10 of this set of values, or n equals 15. To check if the 7th decile value that we get of 94.4 is correct, this condition must be satisfied at most 70%, or 7 over 10. 7 over 10 converted to percent is 70%. Multiply 7 over 10 by 100%, you get 70%. So 70% is 7 over 10. And at most 70% of the sample size, or the number of values 15, are less than 94.4. So we compute 70% of 15 and we check if how many values are less than 70% of 15. 70% of 15 is 70% multiplied by 15, or that's 0.7 multiplied by 15. And 70% is also equal to 7 over 10. So you can write 70% of 15 as 7 over 10 multiplied by 15. 15 divided by 10 is 1.5, and multiplied by 7, you get 10.5. 70% of 15 is 10.5. Rounded up to the nearest whole number or integer, we have 11. This means that 11 values maximum, at most 11 values are less than, should be less than the 7th decile, 94.4. 94.4 is between 93 and 95. And we count the number of values that are less than 94.4. And the maximum number of values that are less than 94.4, or the 7th decile, should be 11. So we count the number of values that are less than 94.4. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have exactly 11 values that are less than the 7th decile, 94.4. Hence, we conclude that the value we get for the 7th decile, 94.4, is correct. Now, if 70% of this data, or at most 11 values, are less than the 7th decile, 94.4, it also means that 30% of these values are greater than the 7th decile, 94.4. We now take two examples for finding percentiles. And as I have said earlier, there are 99 percentiles because you need 99 points in order to divide a set of data or one whole into 100 equal parts, and each part represents 1% of the sample or the set of values. For our first example, we find the 25th percentile of the same set of data arranged in ascending order. In this set of data, the value of n remains 15 because we have 15 values in this given set of data. And the 25th percentile is denoted by P sub 25, where we now take the value of k as 25. Now the value of k for percentile may go from 1, maybe any value between 1 and 99 because we have 99 percentiles. And for k equals 25, we now compute k over 100 multiplied by quantity n plus 1, where n, as I said, is the same 15. And now the denominator of k is 100 because our set is divided into 100 equal parts by the 99 percentiles. We compute this value where k is 25 and n is 15. For k equals 25 and n is 15, we have 25 over 100 multiplied by quantity 15 plus 1. And 15 plus 1 is 16. We multiply by 25 over 100. Using your calculator, compute, multiply 25 by 16 and divide the product by 100. 25 multiplied by 16 is 400. And 400 divided by 100 is 4. You notice that the quotient, the value we get is a whole number. That means that the 25th percentile is the fourth value in this arranged set of values. So from the lowest value in this arranged set of values, we count 4. 1, 2, 3, 4. And the 25th percentile is equal to 74. Again, we check. And to check, we must find the number of values that are less than the 25th percentile. And the 25th percentile means that 25% of the number of values, at most 25% of the number of values 15 are less than the 25th percentile 74. Hence, we calculate 25% or 25 over 100 of 15, the number of values. If our answer is correct, this is the condition that must be satisfied at most 25% or 25 over 100 of the sample size or the number of values 15 are less than the 25th percentile or 74. We now calculate 25%. I will use 25 over 100 of 15. We multiply 25 over 100 by 15. And using your calculator, multiply 25 by 15 and divide the product by 100. Twenty-five by 15 is 375. And we divide 375 by 100, we get 3.75. Three 75 divided by 100 is 3.75, rounded up to the nearest whole number or integer is 4. This means 4 values, maximum. At most, 4 values or maximum 4 values are less than the 25th percentile of 74. Our 25th percentile is 74, and we count the number of values that are less than 74. And we have 1, 2, 3. 3 values are less than 74, and this condition is satisfied. At most 25% of 15, that is at most 4 values, are less than the 25th percentile of 74. And we have actually counted the number of values that are less than 74, and we get 3. This means 4 values maximum that are less than the 25th percentile of 74 means that the number of values that are less than the 25th percentile 74 can be 4 maximum, it can be 3 or 2 or 1. And in our case, 3 values are less than the 25th percentile of 74. Thus, this value of the 25th percentile that we get, 74, must be correct. And if 25%, if at most 25% of the values are less than 74, this also means that 75%, that is 100 minus 25, 75% of the values in this given set of data are greater than or more than the 25th percentile of 74. For our second example in finding percentiles, we find the 83rd percentile of the given set, the same set of numerical values arranged in ascending order. Hence, the value of n is still the same, 15. And for the 83rd percentile denoted by P sub 83, we take k equals 83 and we compute k over 100. Again, the denominator of k is 100 because the percentiles divide the set of data into 100 equal parts. And the value of n is 15. We compute 83 over 100 multiplied by quantity 15 plus 1. 15 plus 1 is 16, and we multiply 16 by 83, and we divide the product by 100. And we find this value using our calculator. 83 multiplied by 16. 83 multiplied by 16 is 1,328. And we divide the product 1,328 by 100. We get 13.28. And we interpret 13.28 as follows. We say that the value of the 83rd percentile is between the 13th value and the 14th value in this set of numerical values. The highest whole number or positive integer less than 13.28 is 13, and the smallest whole number or positive integer that is greater than 13.28 is 14. Thus, we say that the value of the 83rd percentile is between the 13th value and the 14th value in this ascending order of numerical values. Now we find the 13th and 14th values by counting 13 from the lowest value, 57. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 97. And the 14th value is 98. So we now know that the value of the 83rd percentile is between the 13th and the 14th values. Specifically, the value of the 83rd percentile is between 97 and 98. That is, the value of the 83rd percentile is more than 97, and it is 83 over 100 of the distance between 98 and 97. So the value of the 83rd percentile, we are sure, is more than 97. Hence, to 97, we add some value which is equal to 83 over 100 of the distance between 98 and 97. And the distance between 97 and 98 is given by the difference 98 minus 97. And that distance or difference we multiply by 83 over 100. (98) minus 97 is 1. 1 multiplied by 83 is 83. Divide by 100 is 0.83. And 97 plus 0.83 is 97.83. Thus, the value of the 83rd percentile is 97.83. And 97.83 is between 97 and 98. Now we check if this is correct. To check if our value of the 83rd percentile is correct, which is 97.83, this condition must be satisfied. That says at most 83% or 83 over 100 of the sample size or the number of values of 15 are less than the value of the 83rd percentile, 97.83. So we take 83% of 15 by multiplying 83% by 15, or we multiply 0.83, which is 83% in decimal number, by 15, or multiply 83 over 100 by 15. We multiply 83 over 100 by 15. 83 multiplied by 15 is 1,245. And we divide this product by 100. And we get 12.45. Again, if you get the decimal number, take the smallest whole number or positive integer that is greater than 12.45, greater than the decimal number. And the positive integer or whole number that is the smallest positive whole number or the smallest positive integer that is greater than 12.45 is 13. Thus, the maximum number of values that should be less than the 83rd percentile of 97.83 should be 13. Or the number of values that are less than 97.83 may be 12, 11, 10, and so on. But the maximum number of values that should be less than the 83rd percentile, 97.83, is 13. And 97.83 is between 97 and 98. And the number of values that are less than 97.83 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are exactly 13 values that are less than the 83rd percentile of 97.83. And the number of values that should be less than 97.83, maximum number of values that should be less than 97.83 is 13. And we exactly have 13 values in this arranged number of values that are less than 83rd percentile of 97.83. Thus, we say that 97.83 is correct. And if 83% of the values are less than 97.83, we say that 17% of this set of values are greater than the 83rd percentile of 97.83. For your practice, please try the following exercises. For the same set of values or the same set of data, find the 4th decile, the 8th decile, the 28th percentile, and the 76th percentile. You will use the same set of values that we use in our examples. Now we take one last example, but I will now delete the last numerical value, 100, so that the number of values in our set will be an even number and equals 14. We now have 14 values in our set of data, or the sample size n is 14. And for the set of data, we find the value of the 67th percentile, where k now is 67. For k equals 67, we compute k over 100 multiplied by quantity n plus 1. For n equals odd or even number, we always have n plus 1. We always have a plus 1 is a constant. And the denominator is 100 because the required is 67 percentile. If the required is the 8th decile, then the denominator of k should be 10. We multiply k is 67 by n plus 1, and now is 14, plus 1 is 15. Okay, equals 67, n is 14. 14 plus 1 is 15. We multiply by 67 and we divide the product by 100. And we compute 67 by 15 using our calculator. Sixty-seven multiplied by 15 is 1,005. And 1,005 divided by 100 is 10.05. 10.05 means that the value of the 67th percentile is between the 10th value in this arranged set of values and the 11th value. The largest positive integer or largest whole number that is less than 10.05 is 10, and the smallest positive integer or smallest whole number that is greater than 10.05 is 11. We say that the value of the 67th percentile is between the 10th value in this set of numerical values and the 11th value also in this set of numerical values. And we find the 10th and 11th values by counting from the smallest numerical value in this arranged set of values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th value is 90 and the 11th value is 93. Thus, the 67th percentile that we are looking for is between 90 and 93. The 11th, the 10th, and the 11th values. And because the 67th percentile is between these two values, we are sure that the value of the 67th percentile is greater than 90. So to 90, we will add 67 over 100 of the distance between 90 and 93. And the distance between 90 and 93 is given by the difference 93 minus 90. And we multiply the distance between 90 and 93 given by 93 minus 90 by 67 over 100. And 93 minus 90 is 3. Multiply that by 67 and divide by 100. We multiply 67 by 3. 67 multiplied by 3. And you should get 201. And we divide 201 by 100. 201 divided by 100 is 2.01 plus 90, you get 92.01. The value of the 67 percentile is 92.01, and it is between 90 and 93. 92.01 is between 90 and 93. But we still have to check. 67% of the 14 values, maximum at most 67% of the 14 values should be less than 92.01. At most 67% or 67 over 100 of our sample size or number of values of 14 should be less than the 67th percentile of 92.01. Hence, we multiply 67% by 14 or 0.67 multiplied by 14, or you can also multiply 67 over 100 by 14. We multiply 67 by 14 and we divide the product by 100 using our calculator. And you should get 9.38. This tells us that approximately 10 of the values in the given set of values should be less than the 67th percentile of 92.01. 67 multiplied by 14 divided by 100 is 9.38. Again, you take the whole number or the positive integer that is greater than 9.38, but it is the smallest whole number or the smallest positive integer that is greater than 9.38, and that whole number or positive integer is 10. 10 values maximum are less than 92.01. 92.01 is between 90 and 93, and the number of values that are less than 92.01 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 values that are less than 92.01. Thus, the value of our 67th percentile, 92.01, is correct. And if we say that at most 67% of the 14 values are less than 92.01. Then 100 minus 67, or 33% of the set of values, or 33% of the given numerical values are greater than the 67 percentile of 92.01. And that completes our lesson on deciles and percentiles of ungrouped data. In the next lesson, we will take up more measures of variability that include standard deviation, variance, and coefficient of variation.